Hi there! I don't know about you, but sometimes, while working on audio projects, I feel the need to listen to the sound of my new device is making, so I can have a qualitative feeling of what is going on in the circuit. And this is not just a psychological need. Sometimes, you actually need to listen to a sound to appreciate with your senses what is going on. It is something different than just taking measurements with instruments. Oh, don't get me wrong, measurements are an important and essential part of the testing session. Measurements tell you the details of what is going on. But if you just need to tell that something is working, listen to the sound may be what you are looking for. And once you know that something expected is happening, then you can move on and make your measurements to make sure that the device works exactly per the specs that were defined for it. In these cases, it is welcome to have handy a small audio amplifier that will help listening to the sound of your device, and if that amplifier had also a set of different input connectors, it would be even more useful because whatever you want to attach to it, it will always be possible. With that in mind, I decided to build such a small audio amplifier and equip it with a number of different input and output connectors to make sure I can use it in any condition while working on an audio circuit. And of course, I could use this amplifier for a number of other things. Let's see how I did it. The design of this audio amp is made around two integrated circuits, the TDA 2003 and the LM3915. Let's begin from the left side of the schematic. Some of you may have already recognized the IC TDA 2003, which I already used as the main amplifier for both my versions of the Theremin. This IC was very popular at one point in the past as an audio amplifier for car radios. It is capable of generating up to 20 watts of power and is provided with a lot of protection from everything that can happen in a car during the installation of the amp or during its usage. It just needs a little amount of components around it to adjust the wanted parameters and it is ready to work, and it is almost impossible to destroy it. In fact, you can see that I put at its input port just a potentiometer to regulate the amount of signal coming into it and therefore the volume, and an electrolytic capacitor to decouple the input from direct current. Similarly, the output pin goes to the loudspeaker through just another electrolytic capacitor, again to decouple from DC. On the positive of the power supply there are two more capacitors, an electrolytic one and a ceramic, used to absorb spikes in the current used by the amplifier and to filter out the noise going in and out from the power supply, which is external. I did not put an internal power supply to minimize the clutter on the workbench. Whatever I use to power the circuit under test can be also used to power this amplifier as long as the voltage is between 9 and 15 volts. And finally, I added a negative feedback loop between the output and input pins of the amplifier to reduce the range of the frequencies that can be amplified and to prevent auto oscillations that can easily happen on power amplifiers. This feedback loop is made out of resistors R1, R2, R3 and the capacitors C5, C6 and C8. Oh, I almost forgot two more components, R4 and C7. These two components are suggested by the manufacturer of the TDA 2003 and I found that they actually help in preventing auto oscillations. Let's go now to the other half of the circuit. Some of you might have already recognized what it is. Yes, it is a view meter built around the integrated circuit LM3915. This IC makes possible to build a logarithmic view meter with just a few components around it. It can control up to 10 LEDs, and if they are not enough, there is a way to connect two of these ICs together to make view meters of up to 20 LEDs. Once the first LED is lighted up, the IC needs an increase of 3 dB to light up the next LED, and then 3 more dBs for the next and the next and the next, up to the last one. So at the end, with 10 LEDs, one of these ICs can measure increases of up to 30 dBs and 6 dBs with two of them. Looking at the datasheet of this IC, and in particular to its block diagram, you can see that you need to use a resistor connected between pin 6 and pin 7 and to the ground to program the amount of current that flows to the LED, and therefore their brightness. In my case, I used a 220 ohms resistor that, at the power supply voltage of 12 volts, gives 15 mA to the LEDs. This way, whenever the power supply voltage changes between 9 and 15 volts, the LEDs will receive something in between 10 and 20 milliamps, which is perfectly okay to light them up. The other thing that is suggested is to use a resistor in series with the anodes of all the LEDs, in the case the power supply is greater than 7 volts, and this is to prevent the IC from overheating. So I used a 470 ohm resistor that is just perfect to accomplish this task in the whole range of voltages at which this device is going to be powered. The last two components are this 10 microfarad capacitor to absorb the spikes of current when the LEDs turn on and off, and the 2 input RP2, which needs to be calibrated so that all the LEDs are lighted up when the max output of the amplifier is reached. This way, the VU meter will help avoid the overloading of the amplifier. You basically set the volume to 0, then you apply the input signal, and then you increase the volume through the potentiometer, avoiding to increase it further once all the LEDs are lighted up. Anyway, don't worry, if you input more signal than necessary, the IC will just fire up one of its internal protection circuits to prevent it from being burned for too much power either on the input or on the output side. You will just experience a distorted output signal in those cases. So you see, with a very few components, we have obtained a nice audio amplifier with an incorporated VU meter, and this is safe and easy to use in our electronics lab. This time I didn't bother to assemble the amplifier on a breadboard to test its functionality. I know how it works because I already built it several times for other applications, and you can see how that is done in other videos on this channel, for example those on the audio amplifier of both the Theremin V1 and the Theremin V2. However, I did assemble the VU meter on a breadboard because this was the first time that I used this particular IC, and I wanted to experiment a little bit with it to learn all its insides. Here is the circuit assembled on the breadboard. You can see there are just a few components: the integrated circuit itself, the 9 LEDs that I used for visualization. Actually there can be up to 10, but I used only 9 just because I had just around 9 blue LEDs, but you can definitely add the 10th LED if you like. The input of the VU meter is directly on pin 5 of the LM3915. In the final version, I also added a true input on this pin to limit the maximum amount of signal that can reach the LM3915, as we already seen in the schematic description. This is the 220 ohm resistor that defines the current flowing through each LED. And finally, here is the electrolytic capacitor, which helps handling the current spikes when the LED is gone on and off. To test the circuit, I have connected it to a power supply set to 12 volts. Note the sensitivity of the circuits to the noise. As soon as I connected the power supply, the first of the LEDs lighted up, and that's because the IC is picking up the ambient noise. Then I connected the input to my function generator, currently set to provide a sine wave at 800 Hz. You see, as soon as I connected the generator, the LED that was on has turned off immediately, and that's because the function generator was initially set to 0 volt output, and so the input of the VU meter was grounded and it did not pick up noise anymore. When I increased the output voltage of the function generator, you can see how the LEDs started lighting up. The more voltage, the more LED, of course. Note also that the LM3915 can be set to have the whole row of LED lighted up, or only one at a time, depending on the voltage on pin 9. I have chosen to light only one LED at a time, to limit the power dissipation inside the IC. This is obtained by not connecting anything to pin 9. However, you can still see several LEDs lighted at once. In reality, since I provided a sine wave, the single dot went up and down quickly, following the instant amplitude of the wave, so all the LEDs seem lighted up, although in reality they are not. If I had put a DC voltage on the input, you would have seen only one LED lighted up at any given time, as long as there was no noise injected on the input, otherwise there was still more LEDs. There are ways to avoid this issue, but I like to see the whole row illuminated, not just one LED. So this way it's a good compromise, and it looks like it is all illuminated, although only one LED is powered at any given time. Let's now move on to the final assembly of the audio amplifier. The whole device was built on two separate perf boards, the first one for the actual amplifier and the second for the VU meter. I did that so I could put the board with the VU meter directly in contact with the front panel, so that the LEDs can be seen from the outside. I'll show you this later. In the meantime, here is the board with the assembled amplifier already installed on the back panel of the case, and here is the assembled VU meter. As you can see, on the front side you don't see the 3-input and the electrolytic capacitor. Since the 3-input needs to be adjusted once the board is attached to the panel, with the LEDs facing out, I had to put the 3-input on the opposite side so I could access it even with the board installed in the case. The electrolytic capacitor, as you can see, is also on the same side as the 3-input, and that's just because it is too thick and I could not put it on the other side, otherwise the LEDs could not protrude from the holes in the panel. And here is a quick test of the VU meter. I attached it to an old MP3 player and powered it up. It seems to work perfectly. The case for the audio amplifier is small but is rich of openings for the many input and output connectors I decided to add for my convenience, not to mention all the holes needed for the VU meter LEDs and the slits to dissipate the heat produced by the amplifier. So, rather than getting a small aluminum box and spend a lot of time drilling and cleaning all the holes, I decided to make a plastic case with my 3D printer. Here is the OpenSCAD code I used to design the box. I made this available to all of you in case you want to do the same. Just look for the link in the video summary below. The zip file you'll find there contains also the schematic for your reference. The main body is made out of a cubic shell. On the front panel I added the 9 holes for the LEDs, and on each side I added the holes for the appropriate connectors. 2 sides for the outputs, 1 for the power connectors and 1 for the inputs. And then, back on the front panel, which is the top of the case, I added the slits to allow the heat to escape. Then this part of the code is to create some pillars on the inside of the case to make it stronger and to provide a way of locking in place the back cover. You'll see that in the picture in a moment. And finally, here is the code of the back cover, which is a flat surface with some little cylinders to lock in place on the pillars of the case, along with some side wings that help holding the cover together. And here is a rendition of the final object. Note the 2 holes for the connectors that will fit into the loudspeaker I already made some time ago. And here is the front panel with the slits for the heat dissipation, the hole for the volume potentiometer and the holes for the LEDs of the VU meter. On this side you can see the holes for the input connectors. I have a variety of them, so I will always have a way to connect the device whatever its connectors are. Again, these are the holes for the connectors for the loudspeaker I previously built for the lab. And on the other 2 sides you can see the holes for the connectors of the power supply and additional output jacks. And this is the final product, just coming out of the 3D printer. Because it is a plastic box, and because I need some sort of shielding against electromagnetic interferences, I ended up using a conductive paint on the inside of the box, made mostly of copper and silver dust, mixed up in a sort of glue. This kind of paints can be easily bought in electronic components shops, and is also easy to find on the internet. I found this one, for example, on Amazon. The paint sticks to the plastic very well and is quick to apply. Just make sure you use a generous amount of it, otherwise the conductivity will not be optimal and the shield will not work very well. Here is the bottom of the case. You can see how this paint looks like. It seems like a silver coating. And here is the box itself. Be sure to let the paint dry and cure at least half a day, otherwise it will separate very easily from the walls of the box. To ground the inside of the box, since it is not possible to solder directly on it, it's plastic, I ended up using a self-adhesive copper tape. The adhesive is conductive and the other side is just copper that can easily be soldered. To ground the box, I just took a little piece of this tape, soldered on it a little piece of wire and attached it to a side of the box on top of the conductive paint. More on that later. You see, it looks exactly like a little piece of copper foil, and it actually is, but it is very thin and easy to apply. Be careful at handling it though. The edges are sharper than a piece of paper. I also used another piece of this tape layered on the bottom of the box cover, where I will glue the amplifier perf board. 2 advantages for that: the extra thickness, which will make a better shield in the region underneath the board, and the mechanical resistance of the tape, which is greater than the paint, so the glue will not pull the paint apart. And here is what I meant before. The amplifier board sits just on top of the bottom part of the box cover. You may already have noticed from the picture that the board does not sit directly on the copper tape, of course, but instead is kept at a distance through plastic spacers for isolation. So here is what I did step by step to assemble the whole thing. First, as I said, I painted the inside of the box with a conductive paint. Then I let it dry, while in the meantime I soldered the tape with a wire. Actually, I waited until the next next day before moving on, to make sure the paint was really dry. Next thing I did was to stick the tape on the bottom of the cover and then glue to it the amplifier board. While waiting for the glue to dry, I took care of the box itself, attaching all the connectors to it. Once the connectors were in place, I put on the back of the front panel the other board with the view meter and fixed it with a little more glue on the inside of the front panel. And of course, I also attached the potentiometer to the front panel. Note how underneath the potentiometer there is another little piece of copper tape. Again, I did that for robustness of the electric connection. In this other picture, you can see that I added a couple of bare banana connectors to one side of the box. These are the ones that plug directly into the lab loudspeaker. However, since one of the two connectors need to be isolated from ground, I had to scratch out the paint around its hole, enough to avoid unwanted electrical contact, but not enough to reduce the shielding effect of the paint in that area of the box. If you were wondering, here is how the box looks like from the outside at this point. You can see that I already put a knob on the potentiometer for the volume. So in the picture you can also see the ventilation slits, the LEDs coming out of the holes on the panel, the side panel with all the input connectors, and the side panel with the banana connectors for the loudspeaker. For the inputs I use from left to right an RCA connector, a 6.35mm jack, a pair of banana connectors, a BNC connector, and another jack, this time one of 3.5mm in diameter. Going back to the assembly, next step was to connect all the grounds together, along with the box ground. Toward the top of the picture you can see the copper tape with a soldered wire that goes directly to the negative power connector. Talking about the power connectors, at this point I also connected the wires that bring the power to the amplifier board. These wires, like the next that will be attached, end up with a flat connector that is plugged directly to the board without any further soldering. This makes simpler the assembly and disassembly of the amplifier board from the rest, in case I need to make a repair or do some modifications on the circuit. And here you can see also the wires for the amplifier output and the wires attached to the potentiometer. And now in these pictures all the connections are made, all the inputs are connected together, and the same with the outputs. So the last thing to do is to plug the wires into the amplifier board and close the box. However, before closing the box, some testing is necessary of course. So here is the box, still open, but connected to the lab loudspeaker, to the power supply and to a MP3 player. Let's see if it works. Very good. Now that we are satisfied with this quick test, we can finally close the box. And here is how it looks like side by side with the lab loudspeaker. You can see how the banana prongs on the amplifier are well aligned with the banana connectors on the speaker, how they fit together while putting them together, and once they are completely connected. Let's do one last test now that everything is put together. Isn't this a nice, useful little and simple piece of equipment? And I'm sure that you'll be able to find a lot of other applications for this device. Actually, please share how you would use this amplifier in the comments. Before concluding the project, I also put some labels on the box, so that I can remember in the future what is what. I could have done a much better job from this perspective, but since this is a simple and cheap lab equipment, I decided not to spend too much time on embellishments. But of course, if you make this project too, you can make the box as nice as you like. You could even decide to go with an aluminum box, which although requires some extra work, would certainly look much nicer. Anyway, I hope you have liked this device and liked to watch this video. Please give it a thumb up, which will help improving its visibility to others so they can enjoy it too. And also don't forget to subscribe if you haven't done so already, so you will be automatically notified of new videos. A small monetary contribution will also help me in making more and better videos for your enjoyment. Details are in the description below. See you on the next video, and as usual, happy experiments!